So with that, let's go to our next speaker. Aileen Yingst will be talking about science achieved using robotic arms and lessons learned from her experience with operating Mars rovers.
So I've been asked to speak about lessons learned about science enabled by robotic arms. There are, just to kind of set the stage here, there are many official names for the various arms or appendage-like instruments that have flown to Mars. I'm going to use the term robotic arm. If you see other acronyms, there's nothing I can do about that. There are a lot of acronyms in our business, but what I've tried to do is stick a bunch of acronyms at the end of my slide deck, and I'm assuming at some point these will be made public. So those do exist. I will try and explain them as I go. There are many things we've already heard from Sean that an arm can give us that are unique. I've listed three here that I think are three of the most important in facilitating science. Your mileage may vary, but from my experience, these are three of the most important. One is precision placement. That is being able to put your instrument where you want it in a very specific and sometimes very, very tiny area. Proximity placement, that is being able to bring your instrument to the target rather than having to get it from a distance. And then pointing, that is being able to set your instrument in a multitude of different places. And this is all facilitated by the fact that we're talking about instruments with multiple degrees of freedom. So what we've seen from the Mars experience is that the existence, the ability to be able to use an arm expands the number of instruments that can be used and expands the type of science and engineering related instruments that can be used. As Sean said, it's kind of difficult to even picture what it would be like without some sort of mobility. Rovers really gave us scientists' feet, as it were. Robotic arms give us kind of, well, arms. They basically provide us with articulation. And so I'll try and expand on each of these: precision, proximity, and pointing in using examples in the next slides. So as far as proximity and precision, I know that technically the Sojourner rover didn't have an arm, but it did have an articulation device, and it was really kind of the first device of which I am aware on Mars that allowed us to move away from the home vehicle to place onto a target. The APXS and the Mossbauer, which was flown, both of these were flown on the Mir rover Spirit and Opportunity, are both geochemistry instruments, and so they give scientists an in-depth view, a very in-depth view of the geochemistry of a target, and that's something that until we were able to get kind of right up close to a target was extremely difficult to get. I'm showing some of those squiggly lines at the bottom there, not to kind of give you an exact idea of what was found, but more to give you an idea of the fact that they could be looked at, right? Mossbauers either are very, very large, right? Or you need to bring them right close to the target. So the Mossbauer that you're looking at here can fit in the palm of your hand. And if you have something small enough to be able to fly to Mars, then it probably needs to be very close to the target that you're looking at. And the Mossbauers on the Mir rovers allowed us to see things like olivine, pyroxene. These are important volcanic minerals, hematite, which is a water-bearing mineral phase, which for obvious reasons is important. If you have a rock that contains water in it, that suggests that there was enough water on the surface to integrate into those rocks. There are some technologies that can exist without an arm, but they are greatly facilitated by being used with an arm. A camera is just one example. It's the one I happen to be using here. Camera size is controlled by physics. Your lens is as big as it is depending on the resolution that you need. Increased resolution tends to mean increasing the size of your optics, which means increasing the mass of your instrument. But the other way of improving your resolution is to bring the target closer to your camera. And so what you're seeing on the left is a Watson focus test from the Perseverance rover. This was Sol 78. And as you can see, this sort of nested images as you get closer and closer and closer to the surface, and you see more and more and more details popping out. So the MUR microscopic imagers, MSL MOLLE, the Mars Hand Lens Imager, and Mars 2020 Perseverance Watson all use this fact to give us these very, very high resolution, tens of microns per pixel images of the Martian surface. Raman is one of those technologies that can clearly be used, without an arm. We have Raman on the SuperCam instrument on Perseverance. But if you are trying to understand the geochemistry of individual grains, if you're trying to understand the chemistry of individual crystals, if they exist, or individual features that are very small, then you're looking at something that really needs to get close to the surface. What you're seeing here is the first Martian deployment of Sherlock, which contains Raman and luminescence, looking for organics and other rock-forming minerals. You can see the types of data that you're getting over here on the right in these very, very small footprints on the surface. Pointing is a little more subtle. We know that we picture pointing. We know that many of these landers and rovers have a mast where you can mount various instruments. So MUR had both cameras, and it also had a mini test, and that gives you these sort of panoramic views. So in the middle you can see panorama from the Pathfinder landing site. On the top you can see one from the Troy area from Spirit, and then you can see a recent panorama taken on Sol 3167 from Mars Science Lab. And so I don't want to denigrate the ability that articulation allows us to get this sort of contextual view of a site. But an arm has more degrees of freedom than a turning mast. And what that means is an increase in reach for your instrument and an increase of the view shed of any instruments that are mounted on your arm. And so this is just a rogues gallery of pictures, and there are many, many other examples. I just put a few up here, but I wanted to give you an idea of just one camera on one arm on Mars and what it has been able to do. So on the upper left, and these are all from the Mars Hand Lens Imager from MSL, from Curiosity. So on the upper left, this is the REMS boom. That's essentially the meteoritical mast, a set of booms. One of them, we believe, was damaged during landing by a pebble or granule of some sort. This is a diagnostic image that was taken by Molly. The image down below on the left, these are the right wheels of Curiosity. These were taken on Sol 631, and you can see the damage that these wheels have incurred. This camera allowed us not only to look at, examine this damage, but to systematically keep an eye on it during the mission. And so we have regular imaging of the Curiosity wheels just to kind of keep an eye on them and see what's getting worse and what's not getting worse. On the next to that image, you'll see the Chemin inlet. This was taken on Sol 282. Above that, you can see some of the ChemCam hardware. This is the RWeb taken on Sol 808. And then on next to that, you'll see this is the Mastcam M100i, M100 camera, and you're looking down the sunshade of that camera. And if you've got a really sharp eye, you might actually be able to see the optics inside the sunshade. all of these images are important in one way, and that is they're meant to be diagnostic, and they were not initially part of the proposal for Molly or the ideas that we had when we first flew the rover. So all of these things, all of these images, are ways that we can keep an eye on how the instruments and the rover itself are doing. All things that we essentially kind of put together um, on the fly. And then the last image, the one all the way over on the right, I think this one's important. It is not taken by Molly. It is an image of Molly. And we were looking to see if there was any dust accumulation or dust damage on the lens. And for this image would not be possible without an arm, because this is Molly using the arm to face herself towards another camera. But again, impossible without that kind of articulation. This is another pair of rogues galleries focusing a little bit more directly on the science. So if you are able to do precise pointing, you can do these sorts of long-term science experiments like the one on the left, which is the UV sensor over a number of different sols. And then the one on the right, which is the 32 drill holes from the MSL mission taken by Molly. And the thing I want to point out for those of you who are geologists on the line, these are images that are taken straight down, the kind of angle that you would have difficulty having if you're taking an image from above from a 2-meter mast. And so what the arm allows just this one camera, just this one instrument to do, is to take images at a number of different angles, which, if you're a geologist, you know is crucial to being able to understand topography, microtopography in this case, and color and so on. Some of the images I didn't include here are dog's eye views. They're images looking up a stack of very very small layers, but you can see the recessive and the more resistant layer sequence because you're able to move the camera down and look laterally rather than straight down. So the ability to look at all angles is really crucial science that is enabled by an arm. And I'll just point out, yes, I'm an image person, but I suspect this is going to be true for a lot of different instruments as well, that ability to kind of change your angle and look from different ways. And of course, this is, the self-portrait is impossible without the arm. This is the Perseverance rover looking at the Ingenuity helicopter. So there is pictures worth 1,000 words. This is simply impossible without the multiple degrees of freedom we have with the arm. I'll point out too that the science here is actually more than you might think. One of the most difficult things for us on another planet, and this goes for Moon, Mars, doesn't matter where, is understanding scale in the intuitive sense that we humans can do on Earth, and putting objects that we recognize in the scale is really kind of an important part of that analysis. Really quickly, technology that is enabled by an arm. This is an example of InSight. InSight uses its robotic arm primarily to deploy its instruments. That kind of articulation is, enabled by an arm. MER had penetrometers and brushes. MSL and Mars 2020, there's a sampling system. There's the dust removal tool. There's the, I forget what G stands for, dust removal tool. A sampling system, a coring system. All of these things are enabled. They're made possible, basically, by the robotic arms. So a quick summary again, and just you'll note I said something about scale. For those of you who do not work at JPL or have never been to JPL, you might notice that it's kind of difficult to know what the scale of these robots are if you've never really, come up close and personal with them. There's nothing in this image really that gives you a strong scale. A trash can would probably be helpful here. But you can see how important scale is, something that we instantly pick out. So the type of science on Mars that has been accomplished by a robotic arm, that's science that requires or is facilitated by precision or proximity placement, science that requires highly versatile pointing, or science that's facilitated by technology that requires one of the above. So what does that mean for the moon? You've already heard some of this already. So we have been very fortunate that NASA has agreed to combine the sampler instrument with the Heimdall, two of the Heimdall cameras, specifically to maximize the science return on 19C, which is one of the CLIPS missions, rather mellifluously named. And these are Mars examples, but just very quickly, if we had originally had what we had proposed, that would be two fixed mount panoramic cameras that would give us about 120-degree field of view, and then one foot pad mounted imager that gave us about 50 microns per pixel at one point. This is the view that we get with the arm. We have gone down to one panoramic camera, but we get 360 degrees of view. You can get stereo imaging just by doing a translation of the arm and taking the same sequence of pictures. And we also get on that arm one close range imager, which now gives us 35 microns per pixel at 5 centimeters distance with choice of target. So we're not stuck with whatever's underneath us. We can pick the optimal science target. And that, again, is one of the crucial things that you get from an arm. That's my last slide. Thanks very much, everybody, for listening. And I'll check the chat for questions. Thank you.